So in this session, we're interested in taking a look at another example of forming ionic compounds and trying to wrap it up here with a big general summary. So notice a couple of things if you haven't already. Our friend the periodic table is here. And an easy way to use the periodic table is to look at this and say, if I'm thinking about ionic compounds, I want compounds that are elements, that are as far apart from each other as possible. Because elements that are far apart from each other as possible are going to have the most extreme properties, differences in properties. So for example, when we were looking at electron transfer, it should make sense that we're looking for extremes in properties. The property that we're looking at is the ability to lose electrons and the ability to gain electrons. So what we do is when we look at the periodic table, we find the electron losers on this side of the table and the corresponding electron gainers on this side of the periodic table. Again, ignoring the noble gases, we know the noble gases are special because they are, say it together, stable. Okay, so again, these folks here are not going to be doing anything in chemical reactions. They end up being our benchmark. We're interested in locating the gainers and the losers. If we can put gainers and losers together, we've got the possibility of forming a stable ionic compound. So if we look at the columns in the periodic table, it makes a little bit of sense. Again, excluding hydrogen at this point, okay, since it's not a metal. We've got metals in column 1, and notice that all of the metals in column 1 have one valence electron. Therefore, all of the metals in column 1 are going to form ions, stable ions, with a charge of +1. Okay. Correspondingly, all of the metals in column 2, beryllium, magnesium, calcium, strontium, barium, radium, they have 2 valence electrons. They're always going to be looking in ionic bonding to lose 2 electrons. They're always going to have charges of +2. Okay, we skip over the transition metals for right now. Again, they're just a little bit more complicated in terms of how they lose electrons to form stable ions. And we jump to column 13. Column 13 sitting here with 3 valence electrons. Elements in column 13 generally are going to form ions with a charge of +3. All right. We go to the other side. Take a look at column 17. Column 17 is right next door to the noble gases. Everybody in column 17 is going to be looking to gain 1 electron to become isoelectronic with the nearest noble gas. And therefore, everybody in column 17 is going to form ions with a charge of -1. Column 16 all have 6 valence electrons. Again, they are going to be looking to gain 2 electrons to become isoelectronic with noble gases. And therefore, they're always going to form -2 ions. Finally, column 15, they are 3 electrons away from being stable. Their shortest route to stability is gaining 3 electrons. Therefore, they will always have charges of -3. Notice that I excluded column 14. Column 14 is a special column. It's right smack dab in the middle. If you're an element in column 14, say carbon, you have the option, if you're looking to form an ionic compound, of gaining 4, moving this way, okay, or losing 4, moving this way. The reality is that, as a general rule, we're not going to worry about either of these options happening because gaining or losing 4 electrons is a pretty steep bargain, and it doesn't happen very often. These elements generally do not form ions, at least in our simplistic view, and they tend to be more involved in ionic in covalent bonding. So really, if you think about the periodic table, and we're looking at simple binary compounds, which are compounds between 2 elements, binary ionic compounds, we've got sort of a buffet table in front of us, okay? We've got metal ions that we can choose from group 1, knowing they're all going to have a +1 charge. Elements from group 2, we know we're always going to have a +2 charge. And elements from group 13, which have a +3 charge. Correspondingly, for the other side of the pair, we're looking for the electron gainers. We've got gainers that will gain 1 electron and have a -1 charge. We have gainers that will gain 2 electrons and form an ion with a -2 charge. And we have a column that will looking to gain 3 electrons and form ions with a -3 charge. So, a couple of quick examples. Let's take a most extreme example. Let's take aluminum. Okay, aluminum is a metal. It's bordering on the non-metal, but still a metal, and a metal with 3 valence electrons. Again, let's choose our friend oxygen. We haven't looked at oxygen. Oxygen in column 16, 6 valence electrons. Again, oxygen looking to gain 2 electrons. So again, we have a mismatch. We've got an aluminum looking to lose 3 electrons to become stable. We've got an oxygen looking to gain 2 electrons to become stable. How can we make this transfer happen such that everybody is happy? Well, the reality is that electrons cannot be split up. So what we need to do is figure out what is the simplest way for these atoms to get together and form a stable ionic compound. By stable ionic compound, meaning where atoms lose electrons, those electrons are correspondingly gained by another group of atoms to form a set of ions in which the charges on all of the ions add up to be 0. So let's take a look. Obviously, this transfer cannot happen one atom to one atom. This one wants to lose 3. This one is looking to, oxygen is looking to gain 2. If we try to add in another aluminum, it doesn't help things much. Now we've got a total looking to lose a total of 6, still looking only to gain 2. How do we remedy the situation? How about if we add 2 more oxygens? Does this look like a deal? Well, let's take a peek. We now have 3 oxygens, each oxygen looking to pick up 2. We've got 2 aluminums looking to lose a grand total of 6 electrons. So it looks like we've got a nice little transfer here. If we work out the dynamics, we imagine that these 2 aluminum atoms, okay, transfer their total of 6 electrons to 3 oxygen atoms, and we have a beautiful transfer of 6 total electrons being transferred. We have 6 electrons lost over here by the 2 aluminum atoms. We have the 6 electrons gained over here by the 3 oxygen atoms. The result of that transfer is, let me get just a little bit more space here. The result of that transfer is, scroll back up here just for a second, we end up with, each aluminum has lost 3 electrons, so we end up with 2 aluminum plus 3 ions. If you need to right now, you can pause the video and you can double check that an aluminum with a plus 3 charge has 10 electrons and will be isoelectronic with neon and therefore stable. On the other hand, on the other side of the equation here, each oxygen has gained 2 electrons, creating an oxide ion. So now each of these oxygen atoms has been transformed into a stable oxide ion. And again, if you need to check, you can find that an oxide ion, an oxygen with a -2 charge, also has 10 electrons and is also isoelectronic with neon. So again, what we have here is a collection of stable ions. Now, again, the other part of ionic bonding is because we've transferred electrons, we've generated oppositely charged ions. We've got 2 plus 3 ions over here. We've got 3 minus 2 ions over here. Just a note, notice that when we add up all the charges, plus 3 for a total of plus 6 over here, minus 2 minus 2 minus 2 for a total of minus 6 here, that when we put these together, we get 0, okay? And that's the requirement, is that the the sum of the charges of the ions created by the electron transfer has to be equal to 0. And we're always looking for the simplest whole number ratio in which that happens. This compound is going to have a formula of what? Al2O3, and we call it aluminum. We start to say oxygen, but then we chop off most of the name and call it oxide. So the compound's name is aluminum oxide. The compound's formula is Al2O3, and the only help we needed to figure out how that was going to happen was our handy-dandy periodic table. So let me take a pause here, or take a look at this, let you know how simple that is. As we talked about up above, we have the possibility of metals having either a +1 charge. This would be something typical to sodium or potassium in column 1. A +2 charge. This could be calcium, magnesium, or anybody in the alkaline earth family. And then finally, a possibility of a +3 charge. We showed that one up above with aluminum. Across the top here, we have potential electron gainers. And again, the possibilities are either you gain 1 electron and form a -1 charge. This would be typical for chlorine, bromine, fluorine, the elements in that column 17 that are commonly called the halogens. An ion with a -2 charge, just like we showed up here with oxygen. This would be anybody in that particular family, oxygen, sulfur, etc. And then finally, the other possibility is that you have a -3 charge. This would be nitrogen, phosphorus, those elements in column 15. Now, when you put those all together, you find out that there really are only a limited number of possible formulas. If I have a +1 metal ion and a -1 anion, the simplest formula is Mx. This would fit with sodium chloride or potassium fluoride or any compound like that. Okay. If, on the other hand, I have a +1 metal trying to work to combine with a -2 nonmetal, what's the formula going to be? Well, again, I'm going to need 2 of the metals to balance the 1 -2. So the formula for that combination is going to be M2X. Continue that on, stay with a metal with a +1 charge. If I run across a -3 anion, then the formula is going to be what? Well, I hope you're seeing this, M3X. I need 3 of the +1s to balance the 1 -3. Hope that's making sense to you. If not, please pause for a second and go back and think about that a little bit more. In this case, now jump down a row. I've got a metal with a +2 charge, an anion with a -1 charge. The formula here is going to be Mx2. I need 2 of the -1s to balance the +2. In the middle case here, I've got a +2 and a -2. That one's pretty easy. That's going to duplicate the situation where I have 1 ion and 1 ion. In this case, the +2 exactly balances the -2. So that's not a new case. Notice that the formula here is the same as the formula here, even though the ion charges are different. The key is that the charges are the same. Finally, I come over here, sometimes the most difficult example for people. I've got a +2 metal. I've got a -3 anion. I hope you can see that this combination is going to require 3 of the +2s for a total charge, a positive charge of +6, balanced by 2 of the -3 ions, which gives me a total of -6, such that +6 and -6 exactly cancel each other. Finally, the last row here, I've got a metal with a +3 charge, our maximum positive charge that we see in routine compounds. Formula here is going to have to be what? Well, in order to balance that +3, I'm going to need 3 of the -1s. So Mx3 is the general formula. In the middle case here, I've got that 3 and 2 situation, but it's just the opposite of what we talked about before. I hope everybody can look at this and say, okay, if I take 2 of the metals, each with a +3 charge, and 3 of the nonmetals, each with a -2 charge, I've got 2 times a +3, which gives me +6. I've got 3 times a -2, which gives me a -6. The formula has to be M2X3. And then finally, when I've got a +3 and a -3, the formula again is going to be Mx. Okay, so like playing tic-tac-toe, what you notice here is that right down the middle, okay, all the formulas are the same, Mx, Mx, Mx. That happens when the charges on the metal and the nonmetal have the same magnitude. Okay, so I hope that makes a little bit of sense. The possibilities are limited. We really only have 1, 2, 3, 4. We've already counted this one. 5, 6, 7 different general formulas for ionic compounds. All right. I hope that helps. In the next session, we'll just throw in a little bit about polyatomic ions, and then we'll be done with talking about ionic bonding. Hope you're finding this useful.